down to landing. So they've dropped the cover off. They've actually driven a little bit ways away from here. They want a nice flat piece of ground to drop the helicopter. And it's kind of hard to tell, but the helicopter's on its side. Don't ask me how they're going to get it upright. I don't know. But it's basically, this is a rotor, and this is a rotor, and this is the bottom of it here, the top here, and then this is these are the legs, two of the legs, there's two other legs up here, and they'll flip down, and that'll be the four legs that you see here underneath it. And then it's got a little solar panel on top to charge the battery. It's got a little tiny camera in the bottom, so it can take a few pictures as it's flying around. And it is purely a demonstration mission to show that we can actually fly something on Mars. And the atmosphere on Mars is very thin. It's about 1% of the density of Earth's atmosphere. So it needs big rotors at high speed and a lot of pitch on them to get lift to be able to move it around. And it won't be able to fly very long because it doesn't have much of a battery. And these pictures are online. Anybody that wants to go see these can actually just go to this site. We have lots and lots of pictures from the mission. We also have all the pictures from the previous missions are available online for anybody that's interested in downloading them. All right. So now we'll jump into the semi-official presentation. All right. Do you guys see Curiosity in big letters?
Yes, sir.
Excellent. Okay. So Curiosity is a large rover. Spirit and Opportunity were smaller rovers. I'll show you a picture of those in just a moment. This is a view from the Curiosity rover looking toward Mount Sharp. We are actually now at the present time getting up into this hilly area up in here. So this is early in the mission, but we have traversed across here. All this stuff in the foreground is basically sand dunes made of dust, very thin dust. We can't drive through them because they're so thick, we'll just sink. So we had to drive way around and then approach up through here, and we're up in the foothills now. So somebody somewhere is getting paid to drive a giant atomic-powered laser robot on Mars. That's me. That's what I'm doing with my life. So these are the recent rovers that have been on Mars. The one right down here in front, that's a model of Pathfinder that landed with our Sojourner, landed with the Pathfinder mission in 1996. Drove around for about 90 days. They stepped that up to this rover, which is a mock-up of Spirit and Opportunity. These rovers here are actually fully functioning models of the rovers that are on Mars. We use these to drive around in the Mars yard, which is what's behind us here, for testing. You can see this hill over here. We've got different kinds of surfaces on it. We drive the rovers up different slopes with different surfaces to measure how well they'll climb. Now, of course, the gravity on Mars is about 1/3 what it is on Earth, so all of that changes but we use these models to give us estimates of where it can go safely. This is a model of the Curiosity rover. It's very, very similar to what the Perseverance rover is like. They're basically built to print. The wheels are different, but the basically design of the arm, the body, the mass, and things like that are all the same. All right, so this shows you basically how fast these robots go. That's full speed. And you can hear that crinkling noise. That's the wheels. The wheels were made, they had to design this to meet their requirements for weight. They don't have a lot, they want to minimize the amount of weight because every pound takes a lot more fuel to get it to Mars. So they made the wheels, the aluminum on the wheels, very, very thin. You can actually see right here, there are holes in the wheels. We're getting holes in the wheels on Mars because they were made so thin. Fortunately for Perseverance, they've come up with a new wheel design that's a lot stronger, so they're not going to get holes in the wheels. Whereas Spirit and Opportunity, we use the wheels to break rocks. We don't do that with Curiosity. All right. We'll just go on. So this gives you, this is the aeroshell. This is the back cover that it drops off, or I'm sorry, that's on it as it's coming down to Mars. Then the heat shield fits on the bottom of that, and the whole rover fits up inside of there. So that gives you a rough idea of the size of things. And Gale Crater is where we're going. So this shows you where various missions have landed. Opportunity was here, Spirit was here. Mostly they're landing near the equator. We put Viking 2 up here, and we put Phoenix up here. Phoenix actually had, its purpose was to look under the surface to see if they could find ice, which they did. So they wanted to do this studies up near the poles. So this is Gale Crater. You can see it's got there's a crater here with a big mush of stuff in the middle that got pushed up when the impact hit, with a flat area around it. So we're landing in the flat area, and then we're going to drive up into the hills up here. All right, so how do we do our rover driving job? Well, basically, while the rover is awake, we're sleeping. The rover gets done with its activities. It uplinks the data through an orbiter, which sends it down to Earth. Then we spend a bunch of time figuring out what happened to the rover, figure out what the scientists want to do, figure out all the commanding that we need to send to the rover. And then we finally send that up. The rover wakes up just in time to receive that information, and then it goes about its business. So we've got downlink. What's the situation on Mars? We got the planning. We got the sequencing, which are basically command sequences. And basically command sequences are just like writing computer software, only it's going to drive a robot instead of just a computer. And it actually is a special language just for operating our rovers. And we model it, and we make sure it's right and safe, particularly safe. So we do this. This is the downlink room. They look at the images here. They monitor communications. They monitor all the rover status and everything. This is not done in real time again. This just happens when the rover sends down a chunk of data and we go analyze it. We see pictures like this. Here you can see we've used the scoop on the arm. There's a little scoop. You can see the scoop right here. And we've scooped up various samples of this fine soil, which looks like this under the microscope. And we are analyzing it. This is the science team. They sit in this room and they look at pictures and they look at what happened and they plan the next day's activities. We build command sequences with tools that look like this. Basically, you have a list of commands. You have arguments for the commands. We can put comments in them just like software. We go through various reports and things like that that look more like this. And finally, we simulate those commands. So we have a variety of views and tools, 3D simulation and visualization tools, to look at what drives are going to do, to look at what arm operations are going to do. And so here is a simulation of a drive. Here we've attached the camera to the rover, but you can leave the camera floating at one place while the rover moves around. You can also see that the wheels go up and down. We actually model the interaction of the wheels with the terrain. We model the slip. We model the camera moving. We model all these things to simulate what the rover is going to do for the day. For arm operations, we basically create targets on the ground, and then we command the arm motion to go to these various targets. Here we're showing the camera. There's a camera here called MALI, the Mars Hand Lens Imager, and we can model what the images are going to be that it's going to take. And it looks, when we watch it, it looks something like this. This is sped up a lot. So you can see the arm waves around a lot. There's a lot of motion. That was a scooping. We shuffled the data. We dust around to process it because there's a bunch of little tubes in the turret there. And what we have to do is we have to move the dust from the scoop through these various tubes, through a little screen to block out any pieces that are too big. We shake them around. As you can see, we shake and shake and shake. Finally, someday we'll drop it into one of the analyzers. So inside the rover, we have instruments that will analyze the material. And there we're dropping some in. Taking pictures, see what it looks like. All right. That's pretty not much enough excitement for the day. So we put that all together. We write a ton of reports because documenting what we're doing is one of the most important things. We send this data over to the ACE, that they are in the Deep Space Network control room, and they put together these bundles, and the bundles of sequences then get sent up to the rover at the right time using the right antenna at the right frequency, et cetera, et cetera. And in fact, sometimes when we are on opposite sides of the sun, it'll take so long for the radio signals to get there that we are actually sending the radio signals before the rover wakes up. And the rover then wakes up, points its antenna at Earth, and the radio signals come in and it tells it what to do. And all that's got to be carefully synchronized. As I said, since the speed of light time to get one way from Earth to Mars ranges from 4 minutes when we're on the same side of the sun to 20 minutes when we're on opposite sides of the sun, we just can't operate these things in real time. We're not joysticking these guys. We're building these sequences, and then it's going to drive itself all day. We don't know what happens until it gets done and tells us. And if it doesn't tell us, we may never know what happened. And so it goes about its business, and we complete our successful mission on Mars. So we do have a laser beam on the rover, and you can see this is a before and after picture of this rock. These little holes are the ones that were blasted into the rock by the laser. Now this is 8 centimeters across, so these are just a couple 3 millimeters in size. But basically, when the laser vaporizes the rock, the spectrum of light emitted by the vaporized rock is analyzed, and that's used to tell us what the rocks are made of. That's called LIBS, which is laser-induced breakdown spectroscopy. All right, so this is where we landed. So that picture I showed you, remember that I said there were these sand dunes? So these dunes are blocking us from getting into Mount Sharp. So we had to drive all the way down here and through this clear area to get up into here. So we're now getting up into these areas and analyzing some of these areas up in here. So here's another view of it. Now, this is another, so I'm going to give you some more rover driving experiences. So this is all Mars, but now we're talking about some future mission stuff, okay? I've been driving various kinds of robots around JPL for years now. This one was Athlete, the all-terrain hex-limbed extraterrestrial explorer, as it says right there. The purpose of this robot will be to support manned missions. This robot has a flat deck on top. It's supposed to carry cargo, habitats, and things like that. Then it's got 6 legs with wheels. If the ground is smooth, it can drive. If the ground is rough, it can walk. And even if it gets stuck in relatively deep sand, it can actually pick a wheel up, move it forward, put it back down, and do that one leg at a time and actually walk through dusty areas. This image, this was at a field trial up in the state of Washington with some other robots. This shows what a habitat on the back of it might look like. You can see that it's on a slope here. The ground slopes down. And so we have the legs automatically adjust their height to keep the deck flat. So this allows you to protect the cargo so cargo doesn't fall off. You don't risk things falling over and stuff like that by keeping the robot flat as it's going up and down and across hills. Now we're using rubber tires on there. We don't really use rubber tires. So this is what it looks like in real life. This robot actually drives significantly faster than Curiosity does. So it's about moving about walking speed. And while it's doing this, it's constantly adjusting the heights of the wheels to keep the habitat flat. This was a field trial over in Arizona, south of the Grand Canyon, north of Flagstaff. We had to drive this robot 20 kilometers in a week, and we were able to do that. And one of the things I want to point out was this wheel right here. This is a sample space qualified wheel. It's got an aluminum spoke system in the middle. Then it's got these sheets of some polycarbonate or something like that, and some kind of a plastic or rubber tubes in here that are also polycarbonate or something that's space qualified. And then this outer surface right here that's got the tread on it is another very interesting space qualified material. It's called leather. It's actually cowhide that we put on the outside of the wheel to give it tread. And you can see how the wheel flexes here as it goes over rocks and things. So the wheel itself is the suspension that provides shock absorption as we drive over things. Wow, that's the end of that show. So now we'll go to the next one. I have so many, can't keep them all straight. Does anybody have any questions yet? Let's see, where is my...
Yeah, we have one question right now.
Sure, go ahead.
Can Mr. Wright elaborate on space qualification?
Okay, space qualified. All right, so space qualified actually means several different things depending on the context, all right? If you think about space, the differences between space and Earth are you've got a very wide range of potential temperatures. If you're not in this direct sunlight, you're near absolute zero. If you are in direct sunlight, you get very, very, very hot. There's a vacuum. There's no atmosphere. So things like lubricants will evaporate. If you have something that has moisture in it, the moisture evaporates because of the vacuum, dries out. And so for joints like arm and motor joints and things like that, you need to have special lubricants that don't evaporate. For materials, you need things that will maintain flexibility, whether it's hot or cold, whether that won't dry out, if they don't have moisture in them or something that helps add flexibility, that will stiffen up when they dry, and things like that. All right. So let's just show another presentation. Oh, and then another kind of space qualified is radiation. Radiation is clearly an issue with in space. Earth has this ionosphere and the magnetic field around the Earth that protects us a lot from radiation. But when you're out in space, you don't have that. So you need to have computer parts and things that are resistant to radiation. What happens if radiation hits a small wire inside a computer chip or something? The wire is so small that hit of radiation on it sets a little current in it. That current can actually damage the wire, or it can just say, oh, this thing that was a 1 before is now a 0. So you've changed a bit potentially in your program. That 1 bit could say, instead of driving 2 meters, I'm going to drive 200 meters. So there's a lot of backup and checking of the contents of the memory on board the rover as the computer is running the programs to make sure that things aren't changing. All right. So I'll switch to another completely different talk. So this one's going to talk a little bit more about spirit and opportunity, but since I'm a windsurfer, and that's me in that upper right picture there, out windsurfing in Seal Beach, I decided to compare the differences, compare and contrast windsurfing and driving robots on Mars. So basically, they're almost exactly the same. The list on the left is how they're similar. The list on the right is what's different. So basically, whether you're talking about robots going to Mars or windsurfing equipment, you want to keep everything as light as possible, yet as strong as possible. So we use special machining processes to build the aluminum parts or titanium parts for our rovers. And getting them off the ground costs a lot of money. And sure enough, if you want the lightest weight windsurfing equipment, it can cost a lot of money. One of the mantras for the Mars rover program has been test what you fly and fly what you test. So as you can see here, we're driving either Spirit or Opportunity over these different platforms to look at the suspension. You can see how this is called a rocker bogie suspension, and you can see how it adapts the wheel heights to follow the terrain. So it's got a rocker right here. And so as this rotates one way, then it's got a bogie back here, which rotates right here, that allows all 3 wheels to go up and down, not independently, but basically in a certain pattern that allows it to follow the terrain. And it's got a differential inside. So as this goes this way, the other side goes the other way. And that's been shown by years of experience that does the best job of keeping the rest of the robot fairly level. The more level the base body of the rover is, the less likely it is to tip over. And of course, when you're testing windsurfing masts and then you go out and fly them, it's exactly the same thing. So getting up in the air is generally a lot easier than coming down. So this is how Spirit and Opportunity landed. They came down with through the atmosphere, heat shield on the front. This is the aero shell. That's what you saw in the picture in the previous presentation. We pop a parachute. Then we use these rockets to cancel any side-to-side motion. The rover itself is down inside this thing down here, and all these little bumps on it are little airbags. And then we drop it, and it bounces with the airbags to protect it until it finally comes to a rest. And so that process is very hard. Getting it off the ground is easy. Getting it back down safely is hard. Same thing with jumping your windsurfing boards into the air. Here's the one difference, right? If you're a windsurfer, you got to carry your own equipment down to the beach. Whereas with Mars rovers, there's a launch team, there's a cruise team that handles everything between Earth and Mars. There's the entry, descent, and landing team. Those are the people to get it through the atmosphere and onto the ground. And again, they're not actually doing anything, but they're monitoring the systems as it comes down to land. Then we have the impact through egress team. So Spirit and Opportunity came down on landers, and the landers unfolded, and then the rovers had to drive off the lander. So once they're on the ground, that's egress. Finally, they get them on the ground, we get to drive them around. So, as I mentioned before, while the rover's busy, we go off and do something else, usually sleeping or windsurfing. Then we come in, we try to figure out what happened to the rover, what the scientists want to do. We figure out how to make the rover do it. Then we go back to sleep. So the rovers drive themselves. They're autonomous. We give them the commands in the morning. They give us the data back in the evening. And because it's so cold on Mars at night, it ranges from basically freezing in the middle of a warm day down to 100 below 0 Celsius in the middle of the night. We don't do a lot at night. The lubricants, even though they're space qualified, they still tend to stiffen up and be thick when it's cold. So you have to heat the joints up. If you want to move the arm or drive around or something, you have to heat them up to get the lubricants to work. So we tend to do everything during the day and let the rover sleep overnight. Now, occasionally we will warm it up. If we will do some arm work in the middle of the night, if we got the power for it, that's good, but it does take power. Spirit and Opportunity were solar powered, so we were able to keep them. They actually get more power from the solar panels than Curiosity does from its little nuclear generator in the back. But the nuclear generator generates power 24 hours a day, whereas the solar panels are only good during the sunshine. So the total amount of power is greater out of the nuclear thing. So anyway, we do this every day. We have these various tools. This is rows. Seen that before. This shows us the commands, their arguments, comments, what time we expect them to occur, what command sequence they're in. These are just like functions and subroutines in a computer program. We have the hyperdrive component, which it does our 3D visualization of the terrain. It's like a video game. It has a simulation, performs simulations of what the rover is going to do and plays them back so that we can see and validate that it's doing what we want it to do. We have our image browser to go look at the images that have come in, puts them together, mosaics them, and you can then look around. We've got all these various sensors on our robot. Those of you who are do robotics, you'll probably recognize the fact that all of these things, there's these various encoders on all the joints, all the steering angles, wheel rotation encoders and potentiometers, measure all these various angles. We have tilt sensors and inertial sensors, basically gyros and accelerometers. We collect all this data every day. We look at screens like this. I was trained to look at this screen, and all I can remember is that red thing is an error. It's much easier to look at plots of what happens. We're looking at the plots of the rocker angles, the bogey angles. We can see what they look like. We look at pictures to see what kind of problems have occurred, and there's a very, very serious problem in this one. We got kind of dug down into this sand here, and we got a rock caught in the wheel. And that rock jammed it up. The wheel stopped, said, okay, that's done. It sensed that it was trying to use too much power to turn the wheel, and it wasn't turning, and so the whole thing shut down. We were able to get that rock out and keep driving, fortunately. Then we have a plan that looks something like this. This tells us we're going to get command sequences are going to be uploaded to the rover at starting at 9:35. We're going to do communications at during this time period. We're going to nap. We're going to do some arm work. We're going to do some driving, do some science observations, and go back to sleep, and then hand over to the next day at this time. So this is our plan. We have to keep a close eye on our weather. So we have plots that look like this. In this particular case, the red line is how much power we're getting on the solar arrays. So this plot's what we're getting. And this is on a per sol or per day basis right here. And then tau is this blue, which is basically a measure of how clear the atmosphere is. So dust gets blown up on Mars. As the dust thickens the atmosphere, the tau value goes down, and the amount of power you get on your solar panels goes up. So here there's a peak in the tau. I guess I'm backwards, right? So there's a peak in the tau here. Our power level goes down. As the tau gets lower and lower, we get more and more power. So I was backwards on that, right? So you can see this is for the first, starting on about Sol 200 through Sol 2240. So it's 2,000 days on Mars. And we have dust storms that cover the entire planet. So you can see from space, this is what it looks like when it's relatively clear. Here's what it looked like less than a month later when a big planet-wide dust storm had blown up. And got thicker and thicker. And basically we just hunkered down because we didn't have enough power to do anything. But one thing that's really nice is we have what are called cleaning events. So in the spring, just like on Earth, the winds come up, we go windsurfing, and they blow the dust off the solar panels. So here's dusty solar panels, and then here they are a few weeks later after the wind's blown them off, and you can see they're much cleaner than they were here. And you can see our power levels jump up as we get these cleaning events. We've got cameras all over the rovers. We take stereo images. Almost all the cameras on the Mars rovers are stereo cameras. That's so that we can analyze them and build 3D models of what we're looking at. So here's a stereo pair. You notice I put the right on the left and the left on the right. That's not a mistake. That's so if you can cross your eyes, you can look at the right image with your right eye, the left image with your left eye, and you can see 3D, which I can do because I've done it I've had years of practice at it. The interesting thing also is these marks back here. Those are actually where the airbags bounced, because they came down with airbags. So we build these 3D models of the terrain around us. Go back up. This is the actual lander that it came down on. So this is just after we drove off the lander. This is what it looks from lower down. And this is just a triangle mesh, multi-resolution triangle mesh. If any of you ever get into the business of designing computer games, triangle meshes will be a very, very important aspect of what you work on, along with the texture maps that we use to make it look like actual ground out there. So we build these models actually at a resolution where we can model what the rover is going to do with the arm and how close the arm gets to the rocks and things like that. So we build these command sequences. We send them up. We prove them they're right first, of course. We have a ton of meetings to go through, to walk through all the sequences, to look at the animations, to produce reports and things like that. And I'll skip this too, I think. There we go. So wind is very important. So the two left shots are actually shots from Mars. They look pretty interesting, but they show these various wind-driven patterns in the dust out there. And of course, wind completely controls what we do when we're windsurfing. May have forgotten this talk was about windsurfing, huh? So we send those sequences, we produce all our reports, we go home to windsurf. So this is a shot out of the rear end after it landed, right after it landed. This thing right here is not a rock, it's actually an airbag. So we had cables that sucked the airbags in, but they didn't quite pull it in enough. So they drew them in some more. Then this thing over here is a canvas ramp that's supposed to go down the ground so that we can drive off of it. There's a shot of rock named Wapme with our tracks around it. Here are tracks across the Meridiani Planum. I'll give you a little bit of information about these marks here. So turns out the rovers have an onboard capability called visual odometry. So if you drive blind, you just say drive 20 meters in that direction. The rover says, oh, 20 meters, that means I need to turn the wheels this many times, turns the wheels that many times, says, okay, I'm there. But in reality, the rover slips. It can slip left or right. If it's on a slope, it can slip forward or backwards. It just slips because it's slippery surface. So how does it know how much it slipped? Well, it does that by taking a picture of the ground, tracking, finding features in it, driving a little ways, taking another picture of the ground, and then computing how far those features moved. And then from that, it can back compute and say, oh, I must have moved this much in reality. So it updates its knowledge of where it is, and it compensates for slip. The problem is, if you're looking at a dusty area like this out here, there aren't any features that it can track. Well, it turns out these marks in the wheels make in the ground are suitable for it to track. So we drive backwards along here, and we take pictures of the marks and track them, and that's how we use to compute how far we've moved. And occasionally we can get stuck in this dusty area. If we hit a little dune we're not expecting, we can dig ourselves in and get embedded. And by tracking these features, we can tell when we get stuck. So that's what we use these for, but that's not the purpose for them. They were originally there because when Spirit and Opportunity landed, they were inside these landing pods, and they had explosive bolts tying them down to the deck so that it wouldn't bounce around in there. And so these marks are where the holes were in the wheel to lock it down. But it was so useful for driving that we decided to put holes in the wheels of the Curiosity rover, even though it didn't need them. It wasn't tied down to the deck that way. It's actually locked into a jetpack. And then the jetpack's locked to the aeroshell. So they put those holes in it, and but for Perseverance, they decided we didn't use those very much. We didn't need it, so they did not put holes in the wheels for that one. This is what the heat shield looked like after landing. It's the first time we've ever been able to go look at a heat shield that had been used on another planet in a different atmosphere from Earth's. Another shot of it in color. And the interesting thing in there on the far left is a meteorite. There's a meteorite lighting on the surface that we got to look at. All right, I think, is that about my time? So should we call it end and ask questions?
Yeah, you have like about 10 minutes left, so we do have some questions for you.
Let's go.
So Emily asked at 10:29 a.m. for the equipment with hide or skin, so like the leather wheels, how often do you have to replace it due to wear and tear?
So those particular wheels weren't quite up to the job for that big a robot. So we've never used leather on another planet. Okay. But it would be a suitable material to use. And we tore up those wheels. Basically, the weight of the robot was just too much for those polycarbonate straps and things in there that were supporting it, and it would flex too much and end up breaking those. And so the wheels would break down. We never had to replace the leather. It was the inner parts of the wheels that broke down. Since these robots don't drive really fast, they don't accelerate a lot and spin the wheels, we're not going to get a lot of wear and tear on them like you do on rubber on Earth tires.
Another question from Bella. Is there a target date or date range yet for the athlete launch, if it's possible to share?
So the athlete robot was a demonstration. Okay. It was designed to support missions, and then the funding basically has gone to zero. They want newer and better ideas. So I don't know if athlete will ever get to actually fly. Now, there was a period a few years ago where they were thinking about reinstating the program, but I think that's probably not going to happen just yet. However, if you see NASA videos of lunar, and Mars missions, you will occasionally see athlete in there in the videos. because they'll use these old videos that were put together with athlete on it. Okay.
Yeah. All right, and we have another question from Aryan. Is the image browser where you add the color to the pictures taken by the rover, or how do you add color to the images of Mars?
Okay, that's a good question. All right. So the fact is, we have different kinds of cameras. So here in this particular example, you can see this is a gray image. I won't say black and white. It's not really black and white. It's a grayscale image. Okay. And actually, the cameras are high dynamic range. They have 12 bits of resolution versus normal 8. All right. So each pixel has one of 4,096 values. And this is all a function of the chip that we use, the CCD chip that we use to collect the light. So for all the cameras on Spirit and Opportunity were grayscale cameras. However, what we did was they have up on the top here, which may be hard to see in this little tiny picture, but up on the mast, there are actually 2 sets of stereo cameras. One are called the nav cams, navigation cameras. They have about a 45-degree field of view, and they're grayscale. And this image here on the lower left is from one of those nav cams. They're 1024 by 1024, so it's 1 megapixel. However, we also have 2 other cameras called pan cams, which is either panoramic camera or panchromatic camera, because they can take images in color, but they don't actually take color images. What they do is they have a filter wheel, and they have a different color filter that they put in front of the CCD, and each side has 8 different filter wheels. So not only can you see red, green, blue, and actually we don't have red. We have near infrared, green, blue, plus 5 other bands. And both eyes, the left and the right eye, actually have different bands. And so these are science cameras. They want to be able to look at the different frequencies of light being emitted from the surface or being reflected off the surface. And they use that to help them determine what materials the rocks are made of. Okay. And so for Spirit and Opportunity, the color images come from, we'll take one near infrared, we'll call that red, we'll take the green and blue, and then we'll combine those, and that'll be the red, green, blue channels for a color image. On Curiosity, again, most of the images are grayscale, but the science cameras, what are called the mast cams, have color CCDs with what's called a Bayer pattern on them. So each little group of 4 pixels will have filters in front of the individual pixels. There'll be 2 that collect green, 1 for red, 1 for blue, and those are combined to give you a color image. And that's the way a lot of color cameras on Earth work. They actually use a Bayer pattern and combine that to make your color image. Look it up. Bayer cameras. Okay.
All right, so we have some more questions coming in.
Keep them coming.
So Suhaila, sorry if I butchered your name. Suhaila asked if when the rock got stuck in the wheel of the rover, how are you able to get out? Do you already have like a function coded for that scenario, or do you have to give directions on the spot to the rover?
Okay, so we didn't give directions on the spot because again, we can't joystick it. But what we do is we will basically the rock got in there and had to be loose for it to fall in. And then as the wheel turned, it moved the rock up and jammed it against the hub. So basically we figured out a plan where we could rotate it the opposite direction. That would push it down and get it back into the low spot where it's loose. Then we would kind of steer the wheel and try to drive ourselves away from it, mostly using the other 5 wheels to push us and not turning that wheel at all or not very much. And what we do is, here, I'll just go down. Here's a picture right here. Look at that. So when the rovers got stuck here in this very soft, dusty area right here, we built a test bed here on Earth, and we put the rover in it and we spun the wheels to see what would happen. So we do things like this in our test beds on Earth with these same robots that you saw pictures of before in the Mars yard to see what the rovers will do on Mars. So we can jam a rock in there and then go through a series of moves and see if that works to get it out. And if it doesn't work, we try something else. And so we'll try this stuff on Earth, figure out how to do it, and then do it on Mars.
All right, and we have one last question. Kira asked, why is information from Mars important? How did you discover that you needed each robotic part, and how would you construct your robot through experiments?
All right, that sounds like a lot of questions, actually. Yeah. So we'll start with the first one. Why is it important to get information from Mars? And that's kind of an open question. I think everybody probably has a different reason. Some people say it's not important. We should be spending this money on Earth. But the NASA budget is really very, very small. People think it's huge, and it's huge in terms of an individual person, but in terms of the federal budget, it's very, very small. So what we're doing is we're learning about the universe with a small fraction of the federal budget. And some people can say, hey, let's spend it on homelessness. Let's spend it on feeding the people who are hungry. Let's do this. And, maybe those are more important, and maybe they're not. And I think each person is going to weigh that differently and say, yes, I think this is what's important. I personally think it is important to find out what the universe is like. What is the rest of the universe like? Are we ever going to put people on Mars? Do we ever want to put people on Mars? Does it make any sense? Does it make sense to try to develop faster than light travel? Does it make sense to mine the asteroids for minerals and things like that we can't find on Earth or that we're running out of? Things like that. So there are a lot of trade-offs there. And I have my opinions. Most people have their own opinions, and so I think that's a judgment you're going to have to make yourself. And what was the second part of that question? Something about designing robots?
Yeah, it is. How did you discover that you need each robotic part?
So the process of actually building the robot, it starts out as somebody puts together a proposal and says, hey, for $800 million, we'll design this robot. We will build 2 of them. We'll test them. We'll launch them. We'll fly them to Mars. We'll land them, and we'll drive them around. And it's going to cost you $800 million. And we're going to put some instruments. We'll have an arm, and we'll have cameras, and we'll do this and this and this. And then NASA will say, yeah, that sounds like a pretty good deal. Sure, $800 million. Yeah, I can find that money under the couch cushions. Go for it. So then they say, okay, hey, we've got this money. Who wants to propose an instrument? So different universities from different countries. This stuff's all around the world. We have French instruments, German instruments. The ESA, the European Space Agency, provides stuff. And so they all put together a small proposal that says, hey, I'm going to propose to put this particular instrument on there, or others. And then the people who actually have the money, they say, I like that one. I don't like that one. And I don't think you guys can do it. You guys can do it. And they finally kind of just collect the final set of instruments. Now, of course, they have an overriding goal. So for Spirit and Opportunity, their goal was to study geology. So they had a grinder to grind into the rocks. They had an imager, micro imager, to kind of look at the crystalline structure in the rocks. They had a Mossbauer spectrometer and an APXS spectrometer to study the materials that the rocks are made of. Whereas Curiosity is supposed to be a biologist. I'm sorry, not a biologist, a chemist. It's studying the chemistry of the rocks and dirt. Now it's got a different set of instruments. It's got an X-ray crystallography system. It's got a gas chromatograph, as well as an APXS, a rock drill, uses a drill instead of a grinder. So it's got a different set of instruments because it has a different overriding science goal. And then Perseverance is looking more for biology. So it's got a wholly different set of instruments that it's going to use for trying to study biology. Okay.
All right, so we are running low on time, so
Okay.
we will just rush through the last question. How would you construct your robot through experiments? That's the last part of the question.
So, okay. So JPL has done a lot of experimentation. We've built these robots, all kinds of different robots. We've explored with the different kinds of suspension systems. We've experimented with 4-wheel robots, 6-wheel robots, 8-wheel robots. We've experimented with the athlete robot that can walk. We've experimented with with a whole bunch of different kinds of mobility systems. We've experimented with different kinds of arms. The arm is actually built by a company called, if I recall correctly, Honeybee Robotics. If any of you are looking for a job building robot arms, check out Honeybee Robotics. I think they're in Pasadena somewhere. So we've experimented with a lot of different kinds of lubricants at JPL on campus there. We have these big vacuum chambers where we can evacuate it. We can control the temperature. We can put them on tables that actually vibrate, so we can simulate the vibrations of launch or going through the atmosphere for landing. So we can do a lot of simulation stuff, and they just spend years. And people think, that we have a section that deals with the mobility of robots, and their job is to think of these things and write a proposal, get some money from NASA to experiment with something. And so we do all these things, and the lore just kind of lives on at JPL amongst the people, amongst the documents that are around there, and that's what are used to help design the next generation of robots.